Okay, here you have question number 6. In that question, it is said that a metal wire of a constant resistance is used in an electric heater. In order to overload the circuit for the heater, the supply voltages to the heater is reduced to 230 to 220 volts. Determine the percentage reduction in the power output of the heater. Right, power percentage reduction is required. So for percentage reduction, first of all, we have to figure out that what would be the power consumption. That will be V square divided by R. So there is no value of R. So I think there would be not a big deal. But first, we will consider that this is a master formula, and with the help of this master formula, we will be calculating power. Secondly, how to calculate the percentage change? The percentage change can be calculated by the method of change in power divided by the original power. So these are two master formulas. That percentage change is basically equals to total change divided by original value, yani change in power divided by original value multiplied by 100. So if you now this, you will be able to find percentage change very easily. So here I go, that is 230 to 220. So it means the variation will be there, 220 whole square divided by R minus 230 whole square divided by R. This is basically the upper value. That is what? That is your change in power, and then divided by total power, yani original power. That was how much? 230. Original power was how much? 230. This was the actual value. So it is 230 whole square divided by R times 100. So from here, by logic, you can just cancel the R. So the overall value will be 220 square minus 230 square divided by 230 square times 100. So can you please calculate this? Because value is the reduction, so answer will be negative, but you can consider that because we have considered the reduction, that's why answer would be simple as the positive answer. Yes, so what is the percentage?
Yes, just the same. Yeah, I did.
You have calculator, or should I use mine?
No, no, I have.
Okay, calculate then.
Yeah, 8.5%. I did this question. It's this one is right.
Okay, okay, good. So 8.5%. Then
Yeah.
the next one is a uniform wire of the length AB of 100 centimeter. Wire is 100 centimeter length is connected between the two terminals A, terminals of a cell of EMF 1.5 and a negligible internal resistance as shown in figure 6.1. Okay. Uh, Basically, this is the potentiometer question. An emitter of internal resistance of 0.5, 5.0 ohm is connected to the end A of the wire and to a contact C that can be moved. Okay, determine the reading on the emitter for the contact C placed at A. So when you have placed the contact at A, what would be the emitter reading? We have to consider that. For example, your emitter is at this point A. Okay. So what do you think? What should be the value? Is there any voltage across that? Because here the potential, whatever the potential difference is over here, same will be the potential difference at point A. So both the terminals are at point A. I mean, and this end, let me mark it point end X and let me mark it end Y. Both ends are at point A. So overall potential difference would be equal to
Yeah.
zero, right? So you can say that the potential difference is equal to zero. So current is also equal to zero. So its reading is 0 ampere, right?
Yeah.
Then at
I got
B,
this one. B.
okay, for B, when you have connected that at B, then overall entire length is basically across this one. At this is your point B. So when you have connected that B, so the complete this resistor, this 5 ohm resistor, is supplied by 1.5 volt power supply. So that circuit is just shrunk like this, that it is 1.5 volt power supply, and then an emitter is there and a small resistor over here. So it is something like that, that how much basically there is a parallel wire. The resistance of the wire is parallel to that. So let me draw it over here for you, just invert it. But that is 5 ohm resistance, so it is parallel na? So in parallel it would have same 1.5 volts. So you will use that I is equals to V upon R. So V is 1.5 divided by resistance is 5, so it would give you 0.3 amperes. Okay, so your answer will be 0.3 ampere. Is this clear to all?
Yeah. Now, okay, the C part was the confusing one.
Yeah, yeah, I'm just actually why I did not skip the parts so that they are maybe joined together. That's why I just solved all the parts. So it complete
Yeah, they are
question.
joined together.
Yes, using the circuit in B, the emitter reading I is recorded at different distances L of the contact C from end A. Yes, end A of the wire. Some data of the point is shown in the figure. So basically, this is the current in the 5 ohm resistor, and this is the length of the wire. So that is simple. You have to manage that this graph is between the variation in the length and change in current in emitter, which is parallel with the wire. Okay, so what is use your answer in B to plot a data point. Sorry, plot a data point. Uh, Data points on figure 6.2 corresponding to the contact C placed at end A and end B of the wire. Okay, so length is zero. When length was zero, what was the current? Zero. Okay, we have to place 10 over here. And when current length was 100, so what was the current? 0.3 ampere. So this would be the point what you have to plot. Is it clear?
Yeah, which is
Okay.
this way it was weird because if you like it at first, the gradient is like almost the same until 80, and then from 80 to 100, it just doubles.
Yes. So that is basically it would give you a curve, right? Isn't it, na?
Yeah.
Yes. Okay. Then it is said draw a line of best fit for all of the data points and hence determine the emitter reading for the contact C placed at the mid point of the wire. Okay, so once we are going to draw the line of best fit can be uh, you know uh, if I see that um, okay, so this will be basically a line of best fit. But once we are going to draw the line of best fit, the problem will be that the points are not evenly distributed. So that is why if I'm going to draw a curve of bus fit, yani bus fit curve, then I can I can draw a smooth curve like this. One, two, 1 and 2 points below and 3 points above. So it's almost uh, bust fit curve. Okay,
Wait,
and
can do that?
uh, just see 1 point above, 3 points above, and 2 points below. Let me draw it again, because if we say that We can have a curve and a line of burst width. All points above, 3 points below. If we go to the line of burst width, then this can be possible line of burst width, like this. 2 points.
Isn't it too far away from?
Yes, that is why it would be, for example, one point is that three wala point is far away, then two and three. Yeah, these 2 points are closely located. This and this and this, they all are below. So this would not be considered as the line of best fit. That will be a problem. Okay. So actually, at this software, if I'm going to draw the curve of bus fit, will I be able? Maybe one, two, 1, 2, 3. Yeah, it seems that the number of points are evenly distributed over that. Okay. So what is the midpoint of the wire? It's 50, na? 50 centimeter. So at 50 centimeter, when the length is 50 centimeter, your value is almost this. So your answer can be equal to, uh, I mean, that can be equal to 0.1 ampere. Yes, according to this line of burst rate. So you should have some range of data in your answer. I mean, here the reading is 0.10 ampere according to your graph. But let me check the marking same. Ek minute. Okay, let me check it out. Yeah, is there anyone else who have joined me?
No.
Okay. So just it was 2020. Okay. Yes, in the marking same, let's go to the question number 4, 5, and 6. Okay, in marking same, it is said that reasonable line of the curve to the position to the points given correct, giving current as 0.12 ampere with 0.005 ampere accuracy. So 0.005 ampere accuracy mean it can be uh, 0.125, it can be 0.124, something like that. Okay, so here we go. It means we have to recheck the line of best fit. That is okay. That point is far away. Actually, this is a problem. And one more thing, that we are why we are drawing a forced line of best fit. Isn't it that line of best fit
Yeah, it's
are
close enough.
yes. So it is not mandatory to pass it through origin. Yani almost
Mm,
this one.
okay.
Almost this one. Right? So from here we can figure it out that at 50 centimeter mark, yeah, oh, sorry, at 50 centimeter, when the length is 50 centimeter, this is the point, and this point is basically how much, at what values, what is the position of this point. Let me check that position from the graph. That position is basically, this is 50 centimeter. Okay, and at 50 centimeter, this is the position. So can you read that position? What do we have?
1.3.
1.3 exactly.
Yes.
0.1, 1.3 or 0.13?
Oh, sorry, 0.13. Oh, sorry, 0.13. Yeah. Uh,
0.13.
Mark scheme says
Yes.
0.12.
0.12 and plus minus 0.13.
zero
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 five.
five. So it
Yeah.
means we would have a line of best fit. Again, I have to check that
Yes.
0.12 is this one, no?
Yeah. Okay. So it passes through two of them, I guess.
Yes. So
Uh,
that is one point which is basically, you
there's
know,
anomaly.
anomaly. Yes, because
Uh,
that point we don't have any sort of matching with that point, because I have drawn a lot of best fits, but that point, if we are going to manage that point, we are having a forced graph, and forced graph is not allowed for the best fit, right? So it is almost 0.12 position. So yes, it is 0.12 then. Line of best fit can be taken from there. Then use your answer in 2 to calculate the potential difference between A and the contact C for the contact placed at point between midpoint of AB. So when it is placed between midpoint of AB, uh, yes, midpoint of AB, then we have to go through, we have to find the potential difference. Let's check it out. Yeah, when it is placed in between here in the middle, what to find? That is, use your answer in 2 to calculate the potential difference between point A and the contact C for the contact placed at midpoint AB. So at midpoint of AB. So here, let's say this is that point where we are going to make it 0. So for that one, we have to find out the potential difference across. Oh, I see. Yes. So if we have to figure out the potential difference directly, because these all calculations are being done across what? Across the length using the circuit that emitter. Understand that potential difference. Sorry, the different lengths of the distance C and the wire. Some data is plotted. This, and length is given to you. Current is given to you. That all is from this part C. So I can say that answer in two. That is the reading of current. And okay, if this is the value of the current, then oh, okay. Now I got it. That is, I'm just going to draw a circuit for you, just for a better understanding. This is an emitter, and this is basically that 5 ohm resistance, because we don't have the resistance of this wire. That is the problem. If we have the resistance of this wire, it would be fine for us to use the formula of V is equals to IR, or simply I can say that okay, if this is the contact, yani at the midpoint, this is the contact basically at the midpoint. Midpoint is basically here. So
yeah.
here. So technically, if this is 1.5 volt, then at midpoint it would give you 0.75. But the problem is, now this 5 ohm resistor, and this part of the wire is basically in series with each other. You got this point?
So current is same.
Yes. So current is same in these two, and this is one method. So what was the current here? This was 0.12 ampere. So when 0.12 ampere is the current flowing through this, we can find out that okay, whatever the potential difference is between, let me call it point A and let me call it point B, whatever the potential difference is across this resistor, V across the resistor is same as V between AB. This is the logical reasoning behind it. Are you getting my point?
Yes.
right? So I can say that V between AB and AB potential difference is equals to the potential difference across the 5 ohm resistor. Now just calculate that resistance of this, because it has V is equals to, that means V is equals to I times R. So I is 0.12, whatever we have calculated from our gradient, times 5. So the value would be equals to almost 0.6
One six.
volt. Okay, is it clear to you? Now you can find the resistance of the wire as well. Oh, good. 0.6 volt is the voltage. Now explain why. Although the current contact C is at the midpoint of the wire, answer in C is not numerically equal to half of the. Yes, that was the point I have explained to you in the previous part. Okay, that if this is exactly at the midpoint, now this is the midpoint, let's say it is midpoint. So at midpoint the potential difference must be equal to half of that. But if there is no resistance uh, in series with ohm meter, sorry, ammeter, then it can be possible, otherwise no. Got it? Okay,
Yes.
so Yani, here you can say that as the circuit is now behaves like a series circuit, or you can say the potential divider. Okay, and
Yeah.
the half of the wire, half of wire is in series with 5 ohm resistance. Okay, so
Yes.
combinedly, they will have some voltages, or you can say combinedly their resistance, their combined resistance is not half of the resistance of that full wire, right? This is the logical, exact
Yes.
logical answer. So the resistance of circuit, I mean at this time, is not half of the resistance of wire, yani resistance between A and C. Is this clear to you?
Yes. So, yes.
So this was
Just
basically
one more question, not from this paper. Sir,
okay.
I forgot about the formula I equals A N V Q. Was it?